Okay, office hours. We're doing a lot of 129 questions again. Starting with 2.1 number 5. 1.2 number 8 is up there again. We'll talk at least about part C because that one's pretty easy to get to. And if y'all can scoot in a little bit more mixed space, someone can take that chair too. But we're going to start with 2.1 number 5.
Yeah, right there.
If someone can remind me of what that question is.
Yeah, consider a solution that is made from mixing 35 milliliters of 0.22 more AgNO3 and 83 milliliters of 0.22 more Na2SO4. And then there's like 6 different parts, 6 different questions.
Okay, that's funny. Why is this funny to me? 2.1 number 5 and 1.2 number 8, same thing-ish.
Yeah.
Right? So the whole idea here, if I'm remembering that one, if I'm remembering 1.2 number 5 correctly. So the whole idea here is this is like the problem we did, was it the warm-up question on Friday last week? Where it was you mix two, or was that on Monday? I can't even remember. What day is it? No, it wasn't Monday. We did those. It was Friday. It was the warm-up question from Friday, where we're going to look at this. And for me, the important part is that we approach it with the same thing we should approach every chemistry class, even Chem 124. Trying to get his attention a little. Where the first thing we want to ask is, when I mix these things together, what could possibly react? What are the possible ions in solution? So I'm just going to start with saying, okay, if I write down a chemical reaction, I'd have AgNO3 plus Na2SO4. And the typical thing we usually try first, flip-flop, right? Doing a Taft reaction. So I'm going to make Ag2SO4 plus NaNO3. 2 there, 2 there. I know that's aqueous because it's a sodium compound. I know that's aqueous because it's a nitrate compound. I know that's aqueous because it's sodium nitrate. This one I have to look up, silver sulfate. I don't know if it's actually going to form solid or not, but based on the fact that everything else is aqueous, I'm like, oh, this one's probably going to be solid. Right? And we can essentially say, okay, well, if this is, the way I have this written down right now is a precipitation reaction. Which means if I use the KPVT, what's the KSP for silver sulfate? Anyone have that handy?
1.5 times 10 to the negative 5.
Okay, so we had to look that up. Right, but it's a small number, which means in the precipitation way, I'm going to make a lot of product. Solid should form. So when I look at this, I can break it down into kind of 2 steps. I can start with just doing stoichiometry, treat it like stoichiometry. Right, I can do it with stoichiometry where the limiting reactant goes to 0, and then I have to do some equilibrium, because the limiting reactant's approximately 0. It's not actually equal to 0. But we're going to start with just doing the stoichiometry, and we're just going to do the stoichiometry. Now, the reason number 8 from 1.2 and number 5 from 2.1 have so many parts is because it's trying to slowly walk you through, like, okay, think about this step, think about this step, think about this step. If you look at, I think it's numbers, there's one that's a few later, that's like only 1 box. It's like, what's the net amount?
Yeah.
And you have to do, so it's actually all of the steps. You still have to do all the steps, but it's only checking if you get the final answer right. It's not checking along the way for you.
Mm-hmm.
For some reason, that looks easier for people because like the number of boxes is daunting, but it's just so you can check through the process. So I'm not even going to look at what the question is asking about step by step. I'm just going to start calculating things and thinking about how this works, and we'll see if we answer some questions along the way. So I'm going to go ahead. I'm going to start with the stoichiometry. All right, I'm going to do these 2 steps. I'm going to start with the stoichiometry. Let's do the stoichiometry in green. Oh, no, the green's almost out. We'll still do it in green, but we'll do it with this green. Okay, so I'm gonna go ahead, I'm gonna write the same thing. I've got my 2AgNO3 aqueous. I'm gonna have 35 times 0.22. Why do I always lose my calculator? There it is. 35 times 0.22. That's going to give me 7.7 millimoles. Are y'all going to be mad at me if I do millimoles? It's 10 to the minus 3 moles. It's just easier for me. Plus Na2SO4. I'm hoping by this time next week you'll all love millimoles, but no promises. And this is going to be 83 times 0.22. And that gets us 18.26 millimoles. I'm going to do this as a one direction arrow because we know it's mostly towards products. I'm doing it like 127. Like I'm doing it like Chem 127, so it's just going forward, even though we know there's an equilibrium. And that's going to make Ag2SO4. I don't really care about the other stuff it makes, plus some sodium nitrate. Right? I could look at this as common, like net ionic equation, but this is good enough. I have to identify the limiting reactant. I can do it in my head. Right? It's the smaller number, but I have to be careful about that. Right? It's smaller. Oh no, I'm totally fine. It's smaller, and I'm supposed to have twice as much silver as sulfate, and I have less silver than sulfate. So it's just fine. It's the smaller number. So this is my start. My react is going to be minus 7.7 minus 7.7 plus 7.7 times mole ratios. Okay, so we figured out how much solid was made. It's 3.85 millimoles.
Is that 7.7 times 2 over 2 or 2 over
1 of this?
Yeah.
2 over 2.
Why is it 2 over 2?
So the coefficient, you notice the coefficient on bottom is 2 for all of them.
Oh, so it's the, okay.
So, because that's the coefficient of the limiting reactant. This is, we'll get to this eventually on 124. Don't worry yet.
It's really complicated.
We take baby steps to get to it. They've been doing this for weeks.
Because it's multiplied by 2, right? Or is it just multiplied by 1 because 2 over 2 is just 1?
2 over 2 is just 1.
Okay.
Yeah. But
So-
I still put the mole ratio of the coefficient of 2 from that, the coefficient of 2 from that.
Just to remind you that that's what's
There's a
happening.
that there's a mole ratio for each step in the reaction.
Okay.
But it's just multiplied by 1.
I was just gonna say, if you think about it in like dimensional analysis form,
Yeah.
that's what the conversion would be, if you think about what would be on the denominator versus on the numerator.
In dimensional analysis?
Yeah, so it's like
Sorry, I don't know if that's more confusing.
moles
That
of
just
silver
helps me.
nitrate times moles of sodium sulfate per moles of silver nitrate. So the silver nitrate cancels out and you just get it in terms of sulfate. Do you want me to write it out the long way?
No, it's good. It's good.
It's
you know.
important.
I mean, people are you're recording, so I don't want to like be that guy. You know?
Oh, but this
Well,
will help
if-
with the other students.
If you're that guy,
okay.
there's other that guys out there being like,
Okay.
I don't understand it. So let me
Can I
write
plug
this.
my YouTube channel real quick?
No.
Okay.
So quick aside. So let's just take this piece of the calculation real quick and talk about how I do this. So this calculation is saying 18.26 millimoles of Na2SO4. We subtract off the amount reacted, so that's going to be minus 7.7 millimoles AgNO3, but these units don't match up. So we have to use the relationship of the chemical reaction to figure out how they relate to each other. What's the ratio of the relationship? Well, I've got silver nitrate as the thing I'm subtracting, so I'm going to have 2 moles AgNO3 on bottom, that will get me out of my units to silver nitrate and just get me some unitless thing, but that doesn't make sense. It would be like moles of reaction. You could think about it that way. But I want to get it into units of sodium sulfate, and up here I've got 1 mole Na2SO4. So I've got 2 moles of a silver nitrate for every 1 mole of sodium sulfate. So that's where the 1 to 2 comes from. And you notice it crosses out my silver nitrate units and makes it sodium sulfate compared to sodium sulfate.
Okay, and you found the limiting reactant because you looked at the number of moles and you multiplied by 2 and it was still less than the other one?
Divided by 2 and
You
it was
divided
still
by
less
2.
by the 1. Yeah.
Okay.
Because the 2 tells me I need twice as much.
And you just divided by 2 to see, and it was
Yeah.
still smaller by a long shot. Okay,
Yeah.
cool.
And and a lot of times at this point when we're in Chem 129, I do a lot of that check in my head. But there are systematic ways to check what the limiting reactant is in terms of moles of product, moles reaction, or guess and check. If I got a negative number here, I know I picked the wrong limiting reactant. Switch it, do it back, or I did the wrong mole ratio or something else, but still want to go back and check it.
Okay, got it. Cool.
Okay. You'll notice when we go to doing acid-base chemistry and we're doing everything in 1-to-1 mole ratios, I will still have times 1, 1, times 1, 1, times 1, 1, just so I don't forget that there's a chemical reaction happening. Even though times 1, 1 is 1 divided by 1 is really mathematically boring, that unit analysis is still hidden in there. Okay, so we've got our amount of solid that we've produced. We've got approximately no silver ions left in solution. Is it really 0 silver ions left in solution? So how are we going to get the amount of silver ions actually in solution? That solid that's the amount of solid we made is more than the reaction actually makes. So we've essentially, in doing our stoichiometry and ignoring the energy, the equilibrium, we've overestimated our amount of reaction. And now we have to correct that amount of reaction by doing this equilibrium because the limiting reactant is only approximately 0. So I need to write down some numbers to keep this in mind. I'm going to write those numbers in green up here. It's going to be 14.4 millimoles of sodium sulfate in, what's 35 plus 83? That's 88, that's 105? 115. Right, so I did 35 plus 83.
It's 118, Professor.
Oh, 118. Yeah. Thank you. Right, so that's that's the amount of millimoles I have left over, and then I also have 3.85 millimoles Ag2SO4 solid. Not really in the solution, sitting on the bottom of the beaker. Now that I've got those 2 things written down, I can go ahead and get rid of my stoichiometry table, and I can start thinking about the equilibrium that's going to occur. We ready for that?
Could you explain the leftover reactant again in terms of like the solid dissolved in the excess?
This approximate 0 not being 0?
Or what is that 14.41?
So when the chemical reaction happened, all of the silver got used up, and there was some sodium sulfate left over. There was excess sulfate, just floating ions in solution.
Okay.
And we produced some amount of solid sitting at the bottom. So we've got our excess ions in solution after the reaction, and we've got the amount of solid sitting at the bottom of the container after the reaction. Good? Okay. Then we go ahead and say, okay, well, I've approximated my limiting reactant, my silver ions, my silver nitrate to be 0, but I know that can't be true. So I have to do some equilibrium. How are we going to get silver ions back into solution? What do we have as materials left that could put silver ions into solution? The solid. So in this case, I'm going to go ahead, I'm going to look at this silver sulfate solid. I'm going to look at how it goes in some equilibrium to Ag plus SO4 2 minus right? It's going to dissolve. Now, the solution that it's dissolving into, is there zero sulfate? Now, there's approximately 0 silver ions initially. Is there approximately 0 sulfate in solution? No, because we got all that leftover stuff. So we can take this number and we can turn that into a concentration. We're doing 14.4 divided by 118, and we get 0.122 molarity. Not surprisingly, the concentration has gone down from 0.22 because some of the sulfate has been reacted. Some of the sulfate has been removed from solution to make the sulfate. Sorry, the silver sulfate. But there is still some amount of sulfate left in solution. And I think one of the questions is, what's the concentration of sulfate?
Molarity of anions in solution.
Yep, molarity of anions. Oh, at equilibrium?
Yeah.
Well, then we haven't done it yet.
Oh, molarity of excess.
Molarity of excess. So that's the 0.122 is the molarity of excess. For my numbers, your numbers might be slightly different.
I think that it said it was correct.
Okay. I don't know how much I randomized the numbers. It turns out these problems.
These are the same.
Yeah.
I mean, I at least had the same numbers.
Yeah, same.
These problems are really difficult to randomize numbers with because it's really easy to make problems that like don't work if you don't randomize really carefully. So sometimes I'm just like, no, I'm not randomizing. It just creates so much of a headache for me of like, oh, well, now you're in the route regime where that approximation doesn't work, and now we have to do it a different way. Like, so I think we all have the same numbers here. Okay. Now we go ahead. Can you solve this equilibrium table? Yeah, no problem. Right, let's go ahead and do it real quick. Boom, boom, boom. Plus 2x plus x. This is going to be 2x. This is going to be approximately 0.122. Hey, how's it going? Good.
I have much more difficult questions.
Yes. Well, I'll be with you in just a moment. Then we go ahead and we say KSP 1.5 times 10 to the minus 5 is equal to 2x squared times 0.122. We solve that to get x is equal to 1.55 times 10 minus 5 divided by 0.122. 5. Did you say 5.6 times 10 minus 3?
5.5, but yeah.
5.5. I made a mistake in my calculation, and I didn't feel like retyping things in.
I think that's why I did it really fast.
Well, I did 1.55,
Oh.
and I wasn't supposed to, but I didn't feel like typing it in again. So you got 5.5. Was there another digit on there? 5.5.
No, it was 5.54.
5.54. That's great.
After you
5.54.
divided by 1.22, did you just divide by 2 to isolate that x? Or
Square
divide by
root.
4. You divide by 4.
And then took the square
And then
root.
took the square root?
I took the square root and then divided by 2, but it should come out to the same thing. Hey, come on in. Have a seat. Make yourself comfortable. Let me try again. 1.5 times 10 to the minus 5 divided by 0.122.
Sorry. Yeah.
Square root divided by 2. 5.54.
Okay, well, what am I doing?
1.5 times 10 to the minus 5 divided by 0.122.
Mm-hmm.
And then you got order of operations. You can either take the square root or divide by 4.
Divide by 4 is what I did earlier.
Okay, divide by 4 and then take the square root, and that should be x.
Oh, she's just. Okay, yeah, no. Yep.
You got it?
I just didn't associate scientific notation for a second.
Oh, gotcha. Okay, you got 0.000.
Yeah.
You got 0.005.
I
Yeah.
panicked and I was
Same,
like,
same,
this
same.
is the same.
Okay, so that's our x value, and then we can say 2x is equal to 2 times that number.
1.11 times 10 to the minus 2.
1.11 times 10 to the minus 2. And that's going to answer the other parts of that question. Right, the question is going to ask, what's the concentration of, what's the excess reactant concentration? We got that. Next question is,
Was it valid? Was the X approximation valid? You just do it.
Yeah, I think so, right? 10 to the minus 2 is close to not being valid, but I think it's fine. It's going to be like, well, depends on who you ask. This is going to be like a 7% error, but that's okay in this class. So X small approximation looks valid.
Can you write out the check? Because I was a little bit confused.
Yeah.
Why we didn't.
So what I'm
Why we
going to
didn't
do is I'm going to take my X values. I'll take my 2X value because I've got, oh no, just X. Oh no, so we're fine. It's going to be 5.5 times 10 to the minus 3 divided by 0.122. I'm going to figure out what number that is. And that's going to be 0.045. Not technically a percent error, but a percent difference. 4.5% difference, we're probably fine.
I was just wondering why we use the X and the initial concentration instead of the KSP over the initial concentration.
Like they do in the textbook?
Yeah.
So the way that the textbook does it is really only valid for 1-to-1 mole ratios, and is great if we're doing weak acid equilibrium at initial conditions. Doing this kind of check your percent difference at the end is more applicable, right? Because they also have it set up so it's like you take the ratio and see if it's greater than 400. And that's, the 400 comes from 1/0.05 squared. So it's specifically looking at a 5% error.
I see. All right.
So from this we can be like, okay, yeah, 4.5% difference, that's less than 10% difference, we're fine for this class. What else does it ask?
Moles redissolved solid.
So the moles redissolved to solid is, well, how much silver ions do we get in solution? That much. Where did that come from? The moles redissolving. So we're going to go ahead and say, well, 2x is a concentration, not a moles. So I'm going to take my concentration. I'm going to do it in black. I'm going to take my 1.11 times 10 to the minus 2. I'm going to multiply. I'm just going to switch it to moles because it asks moles redissolved. I'm going to multiply by 0.118 liters. And that will get me.
I'm sorry, why do you use 2x instead of x?
Because the silver, oh, you know what? You're totally right. I should just use x.
Okay.
I should just use x, not 2x. You're correct. 5.5 times 10 to the minus 3. Molarity times 0.118 liters. That will get me the moles of silver sulfate that must have dissolved to put stuff into solution. So I'm going to get 6.49 times 10 to the minus 4 moles. And compared to the original amount that I made, this is 3.85 times 10 to the minus 3 moles. So I thought I made 3.85 moles, but I made 0.649 less than that. Right? I made a little bit less than I thought because when I did the stoichiometry, ignoring the energies, I was just kind of assuming that the reaction energetically drove all the way towards products, and that wasn't correct. There's just a little bit. It's not a ton. It's 0.6 out of 38. Does it ask what percent at any point?
No.
It just asks how many moles redissolve.
And then the net amount of solid produced.
Net amount of solid produced is going to be in grams or moles?
Moles.
Oh, thank goodness. So we're going to do the 3.85 times 10 to the minus 3, the amount that we thought we made, minus the amount that we overestimated by, minus the 6.49 times 10 to the minus 4, and then it's, oh, I just erased it. It's 3.2 times 10 to the minus 3. So we didn't actually make a full 3.85. That was if we ignored the energy of things going on. We actually made a little bit less than that. We made 3.2 millimoles. 3.2 times 10 to the minus 3 moles.
How did you know to use x, the 5.54, for the bottom calculation?
Unit analysis, right? So this x is going to correspond. This x right now is, you know, like moles of SO4 2 minus per 1 liter, and I know it's a 1-to-1 ratio from sulfate to silver sulfate.
Okay.
So I just looked at the mole ratio from my x to my solid.
Why wouldn't it be the 2x for the concentration of silver ions?
It would be 2x for the concentration of silver ions, but not for the amount of solid. So the 2x is still the concentration of silver ions, but for each mole of solid that falls apart, you get 2 silver ions, which is why you've got the 2x there. So the x is in moles of solid falling apart already.
Okay. Because I put in 2x, or the value for 2x, and it still gave me a correct answer. I got 6.53 times 10 to the negative 4 when I put in 2x instead of just x. I think that's why.
Oh,
It accepted.
I would have thought you would have gotten something much larger than that.
No. Or maybe it did.
You should have gotten 1.3 times 10 to the minus. You should have gotten something different.
Or I think, because here's how I did it. Because I used the 2x, the concentration, and I found the moles. But
Oh, you had the 1 to
it's-
2. You had the 1 to 2
okay,
ratio
yeah.
there. So yeah, you still have your 1 to 2 ratio.
Okay.
So you would have gotten. That's like getting you back to x.
Okay.
Okay. Now what I'm going to do, since I've got some other classes to answer questions for, I'm going to pause this recording. We're done with number 5, I think. Did we forget anything?
No, that's everything.
Okay. And I'm going to let you all try number 4 together for a little bit. Wow, magic, the board is erased. Okay, so we are going to do at least the stoichiometry for number 6 on 2.1, because people still think the way I do stoichiometry is a little strange. I agree. I like it. So we're going to do it.
It makes sense. It's just
Okay, so we are looking at, where'd it go? Oh, so we're here, okay. We're doing a solution that's made by mixing 100, can you just read the numbers to me real
Yeah.
quick? 122.3 milliliters
So 0.333 molarity
of
of zinc chloride,
0.333 molarity,
and then 83.57 milliliters of 0.654 molarity.
83.57 milliliters of, what was that?
0.654 molarity of sodium carbonate.
Na2CO. Okay, so we start with just writing down our chemical reaction the way that we always do. I'm going to do the two things together, ZnCl aqueous. I know it's aqueous because it's there, and plus Na2CO3 aqueous. It's in molarity, it's aqueous. I can also look up solubility rules, sodium compound soluble, right? And to predict my products, I just do my double displacement reaction, my metathesis. Flip-flop, right? We just flip-flop. The positives and the positives change place, so I end up with zinc carbonate and sodium chloride. It's going to end up with a 2 out front. That's going to end up... Oh, I was like, oh, I don't have a good compound there, sorry. I was like, oh, I'm about to have an unbalanceable chemical reaction. Then we go ahead and say, we got to look up states of matter. I know that one is aqueous. This one turns out is solid. Now, if we're just doing the stoichiometry, I'm not even going to worry about the KSP or any of that stuff yet. I'm just going to look at my start, my reaction, my excess, or my end, and I'm going to do my stoichiometry step by step. And now, the big thing that I do different is, well, we'll do it 2 ways. So let's start with calculating the number of moles of each thing. So if I calculate the moles of this, I'm just going to do 122.3 divided by... Camera does weird things sometimes. Maybe I bumped it. I'm going to do 122.3 divided by 1,000 times 0.333. And I'm going to get 0.0407 3 moles.
Last time you did it millimolar, right? So
Yeah, I
because
prefer
I'm starting to
millimolar.
use millimolar.
Yeah, go with millimolar.
What? Okay, well, I guess we'll just.
The benefit is it saves you a divide by 1,000 multiplied by 1,000
Yeah.
over and over and over again.
When would I have to? I guess we'll find out as we do the problem. But when would I have to remember that millimolar? Because I did that, I need to. Do I need to change that to?
Not as long as your units are consistent.
Right.
Right.
Okay.
As long as you label and you're consistent at the end, you'll just have an answer in millimoles instead of moles. Sometimes LabPal will ask for an answer in moles specifically, or in grams specifically. In that case, you got to watch out for the milli.
Okay, but then I would just add 10 to the third.
Multiply
Or
by,
10
but
to the
yes.
negative,
Yeah. Yeah, and then we do the same thing here. We do 83.57 divided by 1,000 times 0.654. And we get 0.0547 moles. Right, and I can write those numbers here in my starting amounts. 0.04073 and 0.0547. Start with zeros of those things. Now, the big thing that I do that's different, and we'll do it the way that most people learn in high school. And then we'll see how it's the same. And I'm going to start with, okay, can I tell which ones? I'm going to do the excess one first, just because I think it's more interesting. So I'm going to go ahead. The thing that we learn is starting moles minus reacted moles equals excess moles. Right, and we do this type of thinking for each compound in the stoichiometry. So we have to do a mathematical expression like this for our zinc chloride, our sodium carbonate, our zinc carbonate, and our sodium chloride, if we needed to solve all the things. Now, the reason I like, well, there's lots of reasons I like my way more, but we'll do this way first, and then we'll see how I put it into the table. I also have to change the ink in my pen, because it's out. I've been using the same pens for like 6 years now, and just changing the ink cartridges.
Plastic
Nice.
stains.
I really don't like plastic. Let's not get into it. So my starting moles, if I'm doing my sodium carbonate, that's going to be 0.547. My reacted moles is going to be my limiting reactant. I just did by inspection, I could tell this was limiting reactant because it's a 1-to-1 ratio, and so the smaller number is limiting. So I'm going to do minus let me do units as well. 0.547 moles Na2CO3 minus 0.0407 moles ZnCl2 times my mole ratio, which is going to be 1 mole of Na2CO3 for every 1 mole of ZnCl2. Right, here again, we've got our boring mole ratio, we're multiplying by 1. But it's changing the units. So I do all of this math, and what I do is instead of doing it in a like a line like this, I set it up so it's 0.547 minus 0.0407 times 1-to-1. And then I have my total going this way. And I'll tell you that there's a couple reasons why I prefer that method. It saves space. It saves, well, there's one really big reason, but it saves space. It allows us to do all 4 at the same time. It changes the way we think about the math to some degree, but we still get the same numbers. The thing that makes it a little bit dangerous is you'll notice with my saving space, I get pretty sloppy with my units. And so if you're not really comfortable with the way that the unit analysis and cancellation is happening, that can be something that gets you in trouble if you don't know what's going on there. But this is just 0.0547 minus 0.0407. I dropped a digit there. And we get 0.014. If we forget about the 3, which I don't feel like carrying the extra digit right now. And this is going to be moles of Na2CO3 excess. Now, I do the same calculation again for my 0407, for my zinc chloride. 0.0407 moles ZnCl2 minus 0.0407 moles ZnCl2. Now here the mole ratio is kind of pointless because I'm doing 1 mole of ZnCl2 for 1 mole Zl. Here I'm actually just multiplying by 1. The unit change doesn't matter. I still do it just because if I don't do it consistently, I always end up forgetting someplace. Even though I know this is a pointless multiply by 1, I still put it. So my reaction step is minus 0.0407 times 1 to 1. Notice it's the same math. I'm just changing the way I'm organizing it. That gets me 0. Everything in this column for the zinc chloride is in units of zinc chloride. That's moles of zinc chloride. That's moles of zinc chloride. That's moles of zinc chloride. Everything in this column for sodium carbonate, that's moles of sodium carbonate. With the mole ratio, that's moles of sodium carbonate reacted. And here's my moles of sodium carbonate excess, right? Everything in the column is in moles of sodium carbonate. The other reason, the real reason I like this is because it allows me to think about the chemical reaction more in the process of the chemical reaction. I think about where I start, and I think about everything that starts first. Then I think about everything that reacts at the same time. I don't think about this thing reacting and this thing. I think about every step of the reaction at the same time. These things get used up. At the same time, these are getting produced. Right, so I think about all of the reaction. These materials getting used up, that's why they're minuses. These materials getting formed, that's why they're positives. And that lets me think about all of the reaction at the same time, rather than needing to think about the reaction in kind of 4 separate steps, even though they're all the reaction. And so for me, this kind of table really puts me more in the mindset of what's happening in the beaker.
Okay.
That's the real reason. So I like it mostly for conceptual reasons, although it is faster, more condensed space. We just have to be careful because, and you'll notice I label my units at the end because the number one mistake that happens with this is if you lose track from doing a stoichiometry table and an equilibrium table, you mix up moles and molarity. And that is bad. Right? So you've got to pay attention. You've got to, that's why I always still label start reaction excess. I used to call it end, and then a student said you should start calling it excess so that it can be stress. So you got ice tables and you got stress tables.
Is the one in the denominator the limiting reactant?
Yeah.
Okay.
And it doesn't really matter because they're all one-to-ones. But it matters over here if we wanted to know how much sodium chloride was in solution, but as spectators, we don't actually care. So so that's the stoichiometry for the start of it, right? And this is the part that you had a hiccup on, right? So we've got the amount of zinc carbonate formed. You got that bit. But there's still carbonate left in solution. So when we go to do our equilibrium step for this, for problem 6, and we say, okay, this 0 is not really 0, right? That 0 that's not really 0. This reaction, we've overestimated how much this reaction is going to happen because we didn't take the equilibrium into account when we did the stoichiometry. I really didn't do this as a double arrow. I did this as a single arrow, and that's wrong. It's not very wrong, and that's really the question this is trying to get at is, well, how wrong was that? Was it very wrong, or was it minimally wrong? Now, on 1.2, we saw examples where it was not really wrong, right? You ended up with like 0.001% error. It's like, yeah, no, 127 stoichiometry was close enough. We didn't need equilibrium. But we saw was it number 5 we had the 10% error?
Yeah.
In number 5, that equilibrium was significant enough that we actually had a noticeable error in how much solid we would predict. And in number 4, I think we only had like a 5%, we had like a 4% error, almost a 5% error. Okay, in this class, if you're working in some industry where it's like, hey, if you change our profitability by 4% because you made a mistake, massive, right? When you're dealing with companies that do like hundreds of thousands of kilograms of production, a 4% error is like an extra 1,000 kilograms of production or missed production. So 4% errors matter to them. In our class, I'm like 10% is good enough because it makes the math easier, because like 10% is easy to do in my head. Other places, that matters a lot, right? 1% errors matter to people in different industries and different environments. What's your major?
Bio.
Going into medical?
Mm-hmm.
Yeah, 1%, like 5% error is too much in a lot of systems, because 5% error in a medication can cause serious side effects. So in the future, you might have classes that are like, you have how much percent? And oh, that's not okay, right?
Mm-hmm.
Our class, we're like, 10% error, good enough. So it's something to be aware of, and to like kind of like, this is like, okay, how can we take that into account? So let's see if this problem has too much percent error or not. And now to figure that out, I'm going to go ahead, I'm going to do the same thing I did last time, and I'm going to take these blue numbers, these leftover numbers that I need, I'm going to write them down, and then we'll do the equilibrium. So the numbers that I need from the stoichiometry are, I need that I have 0.014 moles Na2CO3 in, what's this total amount? What's 122? Let me get the total volume. That's the 122.3 plus the 83.57, 205.87. And I have 0.0407 moles zinc carbonate solid. Right, that's the part I need from the stoichiometry. We could ask other questions about sodium chloride and all that stuff, but for this problem it doesn't matter. So we can go ahead and get rid of. I should have asked before I erased all that. Did that explanation for how my table works, did that help?
That made a lot more
Cool.
sense. Thank you.
I mean, and in my head I'm like, I did it the first day, but that was so long ago. There was so much happening on the first day. Like we did the syllabus and stoichiometry on the first day. Come on. Okay, now we have to do the equilibrium. We know that is it the zinc? The zinc concentration should not be 0. Where does the zinc get into solution? From these two things that are left over, how do we get zinc into solution?
The solid?
The solid must be dissolving some. So I'm going to have my zinc carbonate solid disassociating now with some equilibrium into zinc 2 plus aqueous and CO3 2 minus aqueous. Now, my zinc concentration is approximately 0. That's what we're trying to fix. My carbonate concentration is not 0. My carbonate concentration is going to be this 0.014 divided by 0.20587, right? My moles of sodium carbonate divided by the total volume. I can't wait till we switch over to millimoles for everything. And that gets us 0.068 molarity. So notice my molarity from where we started with the carbonate is way down. It's like 10 times lower than when we started. That makes sense though, because we reacted a lot of it away. So we've got that 0.068 molarity. And then this time I'm doing initial change equilibrium. So I've got units of molarity, not units of moles. And that's the main thing we have to be careful about, is that switch from moles to molarity when we're doing equilibrium. We got plus x, we got x, we've got approximately 0.068. I should really look at the KSP value before I start trying to make the x a small approximation. What's our KSP value for this?
1 times 10 to the negative 10.
Okay, now I feel good making that approximation. Because I look at this and I'm like 0.068, that's kind of small, but not compared to this.
Mm-hmm.
Right? In chemistry, small is a relative thing. Right? Like, if you're at a buffet and you're eating a small meal, like, small is different than if you're like at a fancy restaurant eating a small meal, because the portions are tiny. Small is relative, right? This is 1 times 10 to the minus 10 is really, really, really small. 0.068 looks massive compared to that KSP value. So I go ahead and make the x a small approximation, and then I just have 1 times 10 to the minus 10 is equal to x times 0.068. Well, that's easy to solve. Oh, and it's going to be really small. 1 times 10 to the minus 10 divided by 0.068. We get x is 1.47 times 10 to the minus 9. And so that is how much zinc concentration, units, very important. Make sure we know what we're doing. Don't get our moles and our molarities mixed up. That is a really small concentration. That's the concentration of zinc ions left in solution. That concentration of zinc ions left in solution. So we went from a concentration of 0.333 down to a concentration of 1.47 times 10 to the minus 9. Approximate 0 wasn't that bad.
Yeah.
What else does the question ask us to do?
It says molarity of carbonate anions in solution.
Oh, 0.068.
Okay. And then the net amount of solid produced.
Now the net amount of solid produced in moles or grams?
In moles.
Okay, so to get the net amount of solid produced, I have to take this, let's do one more mathematical step. I'm going to take this 1.47 times 10 to the minus 9 moles of Zn2 plus per 1 liter. I'm going to multiply by 1 mole ZnCO3 per 1 mole Zn2 plus. I usually do this step in my head, but since we're making a video and trying to be consistent with our units, I figured I'd just write it out, right? You're just multiplying by 1. I do it in my head usually. And then I multiply by 0.20587 liters. And that will get me the moles of zinc carbonate that broke apart. Now, am I expecting a big number here? Oh, no. 1.47 times 10 to the minus 9 times 1 times 0.020, whoop, I got a 0 there, 0.20587. I didn't give myself enough space, so I'm just going to do, that gets us 3.026 times 10 to the minus 8 moles. So I take my 0.047 and I subtract 0.000000003.
I'm sorry, can you repeat that?
I take my moles I produced, which was too big, and I subtract off that amount. And I'll talk about the zinc carbonate kind of a couple different ways. This zinc carbonate, you can think of it, I sometimes call it redissolve. Right? That's to try and talk about it in terms of like the overestimation. Sometimes I will call it the zinc carbonate not formed. Same idea, right? Because it's not like it forms and dissolves. It's just on paper, this is the amount that we overestimated by. Now, you can go ahead and do that subtraction. The answer is just going to be 0.0407.
Okay.
Right? Because I'm subtracting off such a small number. I can plug it in though, 0.0407 minus 3.026 times 10 to the minus 8. I get 0.040699969. 0.0407. For fun, just to give you an idea of like, well, what percentage did dissolve, I can take this 3.026 times 10 to the minus 8, and I can divide by 0.0407, and I can multiply by 100, and I can do flow time. That is 0.12. That's 0.00007% error. So in this case, is the redissolve significant? Is that amount, is our stoichiometry good enough? We didn't need the equilibrium calculation in this case, right? I mean, we did to find out how much zinc ion was left in solution. That's going to be really important for toxic things like lead, arsenic, other things like that, where if you have it left in solution, it's bad. For zinc, doesn't matter, right? That concentration of zinc is not going to be significant. Ooh. Good?
Thank you so much.
Okay. That's it for office hours. I'm going to go ahead and stop this recording. I will post it right now.